Statistics for programmers. As a programmer, you want to know how does your program affect the world. Specifically, when you do a change to the code base and you deploy it, you want to know how does it affect the users and are they happier. If you have many users, then it's possible that you're using already canary deployments and gradual deployments. So let's say you are deploying to 1% of the users and they have received your new feature or an updated feature, and you want to know if you check this 1% of users, if you can deduce from it to the rest of the populations, because you might be doing an experiment. This is actually a 1% of the population, so it's actually a sample. You are sampling the users just like the polls sample the users which are about to elect the new government. The question to ask yourself is this sample good enough? Not only by the percentage, by did you choose the users to be incorporated in this 1% in a good way that would reflect the rest of the population? Can you infer from this 1% to the whole populations of our users? For this, we need to know if our sampling is actually good. We need to check if it's a good sample or not a good sample, both quantitatively and qualitatively. So yes, as programmers, we also need to know the basic statistics about confidence intervals, the central limit theorem, and hypothesis testing. Not only as programmers, in any job you'll have, these are very important concepts to have. And while we are not mathematicians, this information is not too hard to grasp. Unfortunately, the documentation is not that good in the books, and this is why we have this podcast episode in order to explain it in a much clearer way. So, what is statistics and how do we get from our new feature, the new code commit that we did, into confidence intervals and hypothesis testing? We have our actual reality, we have our software, and we have our deployment pipeline. From reality, we get to numbers. We assign numbers to things. For example, we assign heights to people. Okay, we invented these numbers. The people already existed, and then we invented numbers to represent their height, or numbers to represent user satisfaction. If you see the Play Store, you will see numbers from 1 to 5 to represent user satisfaction. So the first phase of statistics is assigning numbers to the real world. And then we're not interested on the whole set of numbers because we cannot really make sense out of it. So we take some representative numbers and sometimes even single representative numbers such as the average or the mean or the standard deviation. This is a single number that we use as a representative to a whole population. It could be 200 million people and one average. This makes things much more clear for us. And then we move on to the next phase. While we cannot really take the average of the whole population, we could, but in many cases, we do not have access to the whole population. As we said, in the feature that we're deploying, we do not want to deploy to the whole of the users. So we take a sample, like 1%, and this is a sample. So we got from reality to numbers, to representative numbers, to samples. And now we need to get back to reality from samples. How do we get back to reality from the samples? Because we are interested in the reality and how we deployed our feature and whether it's working or not. So we take the sample and we try to evaluate whether this sample really represents the reality. We try to evaluate whether this 1% of users that we looked at, whether what we see in them is actually representing the reality. And we do this with confidence intervals, with the central limit theorem, and with hypothesis testing that we are about to see. So let's begin looking at the numbers that we assign to reality. We said we have the reality, then we assign to it numbers. So one number is just the mean. This is the average of the whole population, or the average of a sample, the average of a few numbers that you have. Another number is the standard deviation. The standard deviation is the average distance of each data point that you have from the mean of the dataset. This is basically telling you how far are all the items and all the data points that you have from the mean. How much variation do we have in our data? There is something which is not a number, but it's central to the whole statistics. It's the distributions. For example, the normal distribution, which is even the most frequently used distribution by all means in statistics, the normal distribution is in it, the data is symmetrically distributed around the mean. We can look at a picture and we can estimate how many numbers do we expect to have at a certain part of the distribution. In the normal distribution, we expect about 68% of our data to be within one standard deviation of the mean, and we expect 95% of the data to be around 2 standard deviations of the mean. We won't get into formulas, but we will get into the concepts and the numbers. The z-score is a score that we give to a specific data point. So given a specific data point, this is like the height of the user, or the user satisfaction, 3. Okay, the user satisfaction from this app is 3.5. So we want to convert it to something standard. This is the z-score. So given this input data point of 3.5, we apply a function and we get the z-score, which is a standard deviation of this data point from the mean. How many, the z-score is actually for a specific data point, how many standard deviations is it from the mean? Probability is just a ratio between two numbers. It's just a ratio of a particular event from all possible outcomes. You take all the possible outcomes, you put them the denominator, you take the specific outcome, you put it at the denominator, and you divide them, and this is the probability of an event or a set of events to occur. If we check about multiple events occurring together, then the probability of them would be the multiplication of them. Or the probability of an event B given the event A is a conditional probability, and it has its own formula. Now let's move on to another concept, which is the random experiments. Random experiments is what we expect as the outcome of an experiment. So we do, let's say, a rolling of a die, and the outcome of the experiment is the random experiment. Random variable is the numerical value that we give to the random experiment. So if we roll a die, then 5 or 6 is a random variable, which is the actual numerical outcome that we expect. In binomial experiments, in each experiment, we can expect 2 possible outcomes. It's binomial. Like, would the stock market rise or fall tomorrow? And now to sampling. We said that we have pushed a new piece of code into our code base, and it's reaching customers, and we want to know how many users do we want to provide a new feature in order to know whether the effect that we're going to see in this set of users would represent the whole population. And this is what we call a sample. The basic rule, of course, is that the larger the sample size, then the more accurate and the more confident we are at that sample, giving us a hint into the whole population. The standard deviation of the sample is the average of all the points that we see in the sample to the mean of the sample. So the larger the sample, the larger the n is the number of items we have in the sample, then the standard deviations become smaller. The deviation from the mean would become smaller for us. This basic rules tells us that we want as large a sample as we can. The bigger the sample size, the smaller the deviation, the standard deviation from the mean would be. But of course, we cannot just take very big samples. We want to focus on smaller samples. And this is where the central limit theorems come into play. The central limit theorem tells us this. We can get a glimpse into an estimation of the actual population from a sample. It tells us that given the fact that we are doing a sample, then yes, it encourages us to do samples and it encourages us to take samples in order to estimate the population, for example, mean. So it tells us, the central limit theorem tells us, take more samples. Take more sample groups. And the more you take, the closer you'll get to the population mean. There are some basic concepts about how to do samples. The basic, most simple rule of thumb, and the most accurate and the best rule of thumb is for it to be random. The central limit theorem tells us that we need to trust our samples to the point that we will get direction into the population mean. It asks the question of could we use samples to direct us to the population mean? And we've talked about the background of the central limit theorem, but what does it actually say? So it's talking about numbers, specifically two numbers. If we take samples, it talks about the size of the sample, because the size of the sample is simply the number of, let's say, users that we ask for satisfaction. But we can do this sample multiple times. So let's say we ask 5 users, how do you rate our application? Then we can do this experiment multiple times. We can do this sample 10 times. So 10 times we would ask in each time 5 different users, how do we rate our app? And we would try to deduce from it to the population. But what is its relation to the actual population? So if we do, let's say, 3 sample groups, 3 samples as a whole, and for each of them, we take the average. For each such sample, we take the average of the rating of the app. Then we now end up with a few means, with a few averages. So we had 3 sample groups and we have 3 averages. The more samples we take, the closer we get to the mean of the population, of course. So the more data points that we take in each sample, the central limit theorem tells us that we would get closer to the population mean. This is rule number 1 of the central limit theorem. Take more data points in your sample, closer you get to the population mean, encourages you to take more samples and encourages you to think that the sample mean is getting closer to the population mean, so you can deduce. Another thing that it's saying is that the more we increase the sample size, then the curve of the distribution of what we see is getting taller and narrower. The standard deviation is smaller. So the more confident we get in our results, so it's encouraging us to take larger samples, and also it's encouraging us to increase the number of samples. Because the more we increase the number of samples, we have like more data points in our means, so the curve of the distribution of the samples that we have is more likely to be like the normal distribution. The standard error is the standard deviation of the sample mean. We said that we are taking multiple samples, and then there is the concept of the standard error, which is the standard deviation of the sample means. We take the mean of each sample that we took. Let's say we took 10 samples of the ratings of the users. We calculate the mean of each of them, and the standard deviation of this is the standard error. So we deployed a new feature and we want to know how many users are happy. We can't just ask all the users, are you going to be happy? Are you going to use this feature? So as we don't know the population mean, we are going to answer this new deployment with a sample that we're taking. And the standard error will tell us how much variance do we have from the mean of the samples. And we have a normal distribution. Once we take all the means from all the samples, we always have normal distribution. So the standard error allows us to set a range around the population proportion, which is like we know that it's going to be around this mean, and we know that we're going to be with this error, plus standard deviation and minus standard deviation, which is the standard error. So if we see that in our samples, 68% of the sample is around some kind of mean, then this is one standard deviation, and it could be that we have a problem in the sampling, or it could tell us that the experiment is just different. And then we take the next step into actually connecting the sample to the population, because we only need samples. But how do we connect the sample of the 1% of the users into the actual population? The sample and the population are connected, they are related, because the sample is part of the population. So why can't we connect it? The only question is how big the sample and how many samples do we want? The standard deviation of our samples means, and why do we focus on the sample means on multiple samples? Because it would always result with the normal distribution. The standard deviation of the sample means is the standard error. This is the standard deviation of the actual population divided by the square root of the number of sample size. So there is a basic formula which says standard error equals to the standard deviation of the population. See that the standard error is of the samples, and the standard deviation is of the population. The formula has 3 items: standard error of samples, standard deviation of the population, and the number of items that we have. SE equals sigma divided by square root of n. This is a major formula that connects samples into the population. So you have a formula to connect samples to the population. The formula has SE, the standard error of the sample, sigma, the sample standard deviation, and the number of samples. The confidence interval. The confidence interval is just a number. It's a number that tells us how much confident are we in a certain interval. So it's like a function. You take into the input of the function an interval, and this function would return to you a value. This value would be a percentage. How much confident are we in it? We calculate the confidence interval in a few steps. First, we do a sample. Then we calculate the mean, or sometimes we call it the proportion of the sample. Then we calculate some kind of an interval around this sample mean. And then we assign a number. We calculate a number of how much assured we are in this interval. If we say that we have a confidence interval, if you hear someone tells you, I have a confidence interval of 95%, then this means that if he did this sampling 20 times, in 90 times, he expects it to represent the actual mean of the population, and in one time he's mistaken. So if someone tells you, I expect with a confidence interval of 95% something, this means I meant that if I did this experiment or sampling 20 times, in 90 times I would be correct, and in one time I'm expecting to not be correct. This is the confidence interval. Hypothesis testing. In hypothesis testing, we are trying to discover whether something is real news or fake news. Let's say that we have deployed again our feature to 1% of the customers, and we have seen that the rating has gone up from 3 stars to 4 stars. We want to know if it's real news or fake news. By fake news, we mean there is some kind of a problem. These users were this sample is not representing the real life. It means that this sample we cannot deduce from it that there is a change. Okay, that this sample is not large enough. So is it real or fake news? Is the thing that we have seen that the users have increased their star rating of our tiny app that our one developer created? How likely is it that a new medicine for COVID-19 that made a few patients recover a few days sooner, how much significant it is? Because if users tend to change their star rating of our app every week, then once we deploy a feature and we sample a few users and we see that the star rating have changed, okay, but it's changing all the time. This sampling does not tell us anything. And here we come to the number significant. Significant, did this happen by chance, or is there something into it? Is it fake news or real news? Did something really happen to it and it's not just a chance? If our app changes its ratings week over week, then when we introduce a new feature and we do a test on the sample and we see a change, we cannot deduce anything from it. It's not significant. This happened by mere chance. There is nothing to it. It's fake news. So we gather data in samples and we try to deduce if it's significant or not, if it's real news or fake news. H0 is the null hypothesis. It's the status quo. Nothing has changed. Everything is as usual. It's only happening by chance. If something has changed, it's by chance. H alternative, is the alternative hypothesis, which means something special happened here. It's not a mere change. This is real news. And the significance level is some kind of percentage. Let's say 5% that we say, if we pass this threshold of 5%, well, what is this threshold? We will just see. If we pass this threshold, then if there is only 3% that this would happen, I mean, if actually there was, for the sample that we have taken, for the experiment that we did, there was only 3% for it to happen, and the significance level is 5%, then we say that something weird has happened here. So if the event we have seen has less than 5% chance to happen, which is the significance level or alpha that we have chosen, then we're saying something new has happened here. We have news. We can't reject the null hypothesis. Something might have happened. Something real might have happened. However, if the outcome that we saw as the evidence of the sample of the experiment that we did had chances happening randomly 10%, then the significance level of 5% would mean that we did not really pass this threshold. So we say that it could have been simply happening by chance. here we have also the concept of the p-value. The p-value is talking about the reality. We did the experiment, we saw something happen. The p-value is asking what is the chance that this event would occur by chance. So what is the chance that the users would increase their star rating from 3 to 4 by chance? This is the p-value. The p-value is what is the ratio, what is the percentage, what is the probability that this event has happened by chance. Actually, for the event that we've seen, the significance level is some kind of a threshold that we put. So if we see that the p-value was 2%, but the significance level was 5%, then we say that this event that we have seen, it has a really low probability, 2%, to happen by chance. And as we have set the significance level to 5%, then 2% is smaller than 5%, so we reject the null hypothesis. We suspect that something really has happened, and this is how we do hypothesis testing. So to sum up, we have started with the real world. We have assigned numbers, height of something, star rating of an app, the number of days it takes someone to recover from the coronavirus. And then we do some sampling, and the central limit theorem encourages us to do as many experiments as we can to get many data points. The more data points that we get, the closer we get to the mean. The more number of samples that we do, then the curve of the mean of the means would look much more like a normal distribution. And then we continued with the hypothesis testing, where we look at a specific sample, we look at a specific poll that we do the population, and we ask, how likely was it for this to happen by chance? If it was very likely for this to happen by chance, then we do not reject the null hypothesis. We said everything is as usual. But if we see that the sample, the specific single sample that we did, had a very low probability of happening by chance, or in other words, the p-value, the probability of the experiment and the sample and the results that we have seen, the p-value has a chance of 2% happening randomly, and we have set the significance, the threshold level to 5%, and we say that this event was significant. The p-value is smaller than the significance levels, and therefore we reject the null hypothesis, and we say that our feature has really changed the rating, and it was not a mere chance. We have changed the ratings of our app that our single developer has created, that did not really learn computer science, have created. And what we're saying is that yes, we have done a change in the rating of the app. It's significant, so we move on to deploy this change to more and more users, because we expect that the whole population would benefit from this new feature. So I hope you enjoy this episode of Statistics for Programmers, and I will see you next time.